Hi, and welcome to the presentation. I'm Yotam, and from Technion, Israel, and I'm presenting VCG under Sybil attacks, Bayesian Analysis. It's a joint paper with Ron Levy and Moshe Tenenholtz, and it appeared in AAAI this year. So let's start with the problem statement. So recap on the main concepts that we examine in the paper. So VCG is the truthful combinatorial auction maximizing social welfare. So it has these two nice properties, that it is truthful and has perfect social welfare. False name attacks is an attack method where the bidder not only can change his own valuation when he submits it to the mechanism, but he can actually generate as many identities as he wants, and from each of them submit bids that are whatever bids he wants. And once you open the mechanism to this line of attack, it is no longer truthful. As long as it's not a single item auction. So for a single item auction, VCG traces back to second price auction. And in second price auction, actually, if you submit multiple bids, it doesn't help you. It is basically like setting a reserve price for yourself, which is not beneficial. So with single item, VCG is even false name attack proof. But this is no longer the case with more than one item. You can think of a simple example. If there are two items, let's say two bidders participate in the auction. One of them has a valuation of $10 for the two items. One of them has a valuation of $5 for two items. So if they bid truthfully, the person with the $10 valuation will get the two items. But if the person with a $5 valuation submits two different bids from two different fake identities, one of $100 for one item and one of $100 for the second item, they actually, since the mechanism maximizes over social welfare, it will give the two items to the two fake identities that have a total of $200 valuation for the items. And when it comes to charging them, you can verify that the mechanism would actually charge them nothing for the item. So you would get the two items for nothing, for no price. And in a way, these two bidders are protecting each other. So the fact that the first fake bidder really wants this one item for a very big valuation means that the other fake bidder doesn't need to pay, and vice versa. So so you can see that VCG in the worst case is vulnerable to false name attacks, and the way past literature try to deal with it is by designing alternative auctions so there is a really big body of work by Makoto Yoku and his students about this, which I very much recommend reading. But they also have impossibility theorems that show that you will have to have lower social welfare in this case. So what we try to do in our approach is to look at it not in a worst case analysis, but in a Bayesian analysis. So we assume there is some distribution over the bidder's valuation, and then we want to reestablish truthfulness instead of a dominant strategy as in the regular analysis. We want to establish it as a Bayesian Nash equilibrium. And actually, our results show that in many, many cases, it is a truthful Bayesian equilibrium. There is a truthful Bayesian equilibrium. So let's go into the model. We try to take a simple model that reproduces the problem of the vulnerability to false name attacks. So we take two identical items, single-minded bidders. What it means is that basically the bid, the valuation space is each bidder has a value, whether has a bit of information determining if it wants one item or two items, and it has the valuation per item between 0 and 1. So in the Bayesian analysis, we have some parameter Q. So the preference if bidders want to have one item or two items comes from a Bernoulli distribution over this Q. And there is also some distribution F with support in 0, 1 for the per item valuation. So what you can imagine this scenario is like you have restaurant tickets, or you have movie tickets, or you have maybe one column advertisements or two column advertisements. And the people coming in have the same per item valuation, whether they want one or two. So imagine you're going to the movie. Your preference depends if you're going as an individual or a couple, but the amount you're willing to pay per movie ticket probably is the same whether you go as one or two. So you have this preference over the amount, and you have the preference or the valuation for the per item that you have per item. And in the model, in general, there can be some arbitrary number of bidders. And of course, there are VCG assignments and payments. So this is a VCG mechanism. Okay, so the main definition, the main distinction that we find is that you have this Q star. So let's define formally. Q star is the minimal number between 0 and 1, such that truthfulness is a Bayesian equilibrium when Q is larger than Q star. So where does this come from? Basically, Q star is as much bidders that you have that want one item actually protects the mechanism in the Bayesian sense from false name attacks. So if you remember, the intuition can come from the single item situation where when there was just a single item, the mechanism was false name proof, right? And if you go back to the example I gave, which is where the mechanism is vulnerable to false name attacks, so actually you can see that if the other bidders participating in the auction have different preferences, the example doesn't work, and actually the attacker loses from performing the attack in comparison with the truthful behavior. So this is where the Bayesian analysis comes into play. So when there is enough weight for the bidders that want a single item, the mechanism can reestablish truthfulness as a Bayesian equilibrium. So the first result we have is that when there are two bidders, and it doesn't matter the per item value distribution F, we have Q star is less or equal to 2/3. So whenever you have Q higher than 2/3, you will have a truthful Bayesian equilibrium, and it doesn't matter what is the distribution. But for some distributions, it might be lower. For example, later we will see for the uniform distribution, it's half instead of 2/3. Okay. And then there is negative results. We know that for 3 or more bidders, we can always find a distribution such that Q star is arbitrarily close to 1. And this means that if we try to do a general distribution analysis, we are not able to give very interesting results for more than 2 bidders. And that's why at this point we go to analyze a specific class of distribution, the beta distributions. So as a reminder, beta distributions is a class of distributions that is parameterized by alpha and beta. And it includes, for example, the uniform distribution. And the good properties in our model is that it has a finite support on 0 to 1, and also that it varies. So you can encode very different distributions with it. Okay, what happens once you plug the beta distributions into the analysis? So actually what you get when you do the expectation calculation is you get some polynomial in the valuation. You have some parameters, like you have the valuation, you have the possible line of attack. So all of this can be encoded as variables, and if you go over all possible variables, you get some for the expectation, you get some polynomial, and this expectation is the difference between performing bidding a truthful bid and bidding some line of attack. So if you take this expectation, as long as it's higher than 0, then you have the guarantee that truthfulness is better than this line of attack. And if you prove that the whole polynomial for whatever assignment of variables is higher than 0, then actually you have a truthful Bayesian equilibrium, because any line of attack is less beneficial in expectation than truthfulness. So actually there are algebraic methods to perform this analysis for the whole assignment range. In our case, in our model, we have a trivariate polynomial, so 3 variables. In general, maybe if you do more complex, more complicated, complex is something different, more complicated analysis, complicated model, then you will have more variables in your polynomial. But with these algebraic methods, you are able to prove that given some Q star, the polynomial is always positive. So what you can see in the graph is a summary for some values of parameters and some number of bidders. What are the Q star we attain? And the main takeaway or easy takeaway from this is that you can see that it is bounded away from 1. And also in the development over the growing number of bidders, it doesn't seem to go to 1. And also here you can see the same behavior. It has like this decaying behavior when the number of bidders grow, which is good. It means there is, it seems to have some Bayesian resilience even with a growing number of bidders. And actually we're able to give an even better analysis. So what we are able to notice is that actually there is one special attack that in all the points, all the points that give us Q star, that are the sort of extreme points of the analysis of the polynomial, actually they all share one common attack, which is a very intuitive attack. So as I said before, in general, we consider all types of possible attacks, false name attacks, but there is one kind of intuitive attack where a bidder has valuation, wants 2 items and has some per item valuation theta. Instead of that, he creates 2 fake identities and bids one, like he wants, one of the fake identities wants 1 item with per item valuation theta, and the other fake identity wants 1 item with per item valuation theta, in hope, so the false name attacker hopes that both of them will will win in the mechanism and somehow will pay less. So this is the split attack. Basically, he splits into two. And so all of this, it's not always the best response given the other bidder setup and the behavior of the mechanism. It's not always the best line of attack, but it's the worst line of attack for the mechanism when you do this Q star analysis, in all the cases at least that we checked. So, so for this, because once you have this set of points of the split attacks to analyze instead of the entire polynomial, it's easier to give asymptotic results or results for general n. So we give one such results that if you take the uniform distribution and you take any number of bidders, you will always have Q star at half. So we use some nice techniques for it. I recommend if you go into the paper to read it. We use like this type of hypergeometric identities methods to prove it. And it's probably possible to extend it to other distributions. So we took the uniform distribution, but you could choose other distributions and try to get this analysis. And hopefully if this kind of, we have this conjecture that split attack is always the interesting attack to analyze. So if that's true, then you can have this asymptotic and general results. Okay, I think that kind of sums up the main ideas in the paper. And so I will be happy to hear if anyone has comments, or you can email it to me. And thank you very much. Goodbye.